Assalamu alaikum, dear students. I hope you will be fine. This is the second lecture of the course Signal and System. इससे पहले जो पहला लेक्चर था that was just an introduction of the course. उसमें मैंने कोर्स के अंदर जो टॉपिक्स हम डिस्कस करेंगे वो हमने डिस्कस किया है. आउटलाइन है इस कोर्स की कि इसमें क्या डिफरेंट चीज़ें डिस्कस की जाएंगी और डिफरेंट टॉपिक्स जो हमने स्टडी करने हैं इस कोर्स के अंदर उनके बारे में बात की है. अगर आपने वो लेक्चर नहीं देखा तो मैं आपको एडवाइस करूँगा कि वो लेक्चर ज़रूर देखें. उसकी वजह ये है कि उस लेक्चर में हमने वो सारी टॉपिक्स की बात की है, उन सारे टॉपिक्स की बात की है जो हम इस कोर्स के दौरान कवर करने वाले हैं. सो इस लेक्चर में जो इसके कंटेंट्स हैं इसमें हम डिफाइन करेंगे कि सिग्नल्स जो हैं वो क्या होते हैं, उनकी क्या इम्पोर्टेंस है, उनके जो डिफरेंट एस्पेक्ट्स हैं. सिग्नल्स को बेसिकली डिफरेंट बेसिस के ऊपर क्लासिफाई किया जा सकता है, उनको डिफरेंशिएट किया जा सकता है एक दूसरे से. सो उसमें से कुछ जो उनकी क्लासिफिकेशंस है उसके बारे में हम आज के इस लेक्चर में बात करेंगे. कुछ मज़ीद चीज़ें जो फर्दर सिग्नल्स को जिस बेस पे क्लासिफाई किया जाता है वो हम नेक्स्ट लेक्चर में बात करेंगे. लेकिन आज के इस लेक्चर में हम इवन सिग्नल्स के बारे में, आर्ट सिग्नल्स के बारे में और जो है वो इवन आर्ट डिकम्पोजिशन सिग्नल्स की किस तरह से की जाती है, पीरियाडिक सिग्नल्स के बारे में और एपीरियाडिक सिग्नल्स के बारे में बात करेंगे. इसी तरह से एक और क्लासिफिकेशन जिसपे सिग्नल्स को एक दूसरे से डिफरेंशिएट किया जा सकता है वो कंटिन्यूस टाइम सिग्नल्स हैं और डिस्क्रीट टाइम सिग्नल्स हैं. सो हम इसके बारे में भी आज के लेक्चर में बात करेंगे. सो वी विल स्टार्ट with the basic definition of a signal, what is a signal, and then we will talk about different types of signals. When we talk about the types, these are the classifications according to which signals can be divided into some categories like even, odd, periodic, aperiodic, continuous and discrete signals. So let's start. Signals are basically everywhere around us. If for example we talk about the speech signal, whenever human beings communicate with each other, whether that communication is face to face or even through this sort of video message or some audio message or any other by any other means, जब भी हम एक दूसरे के साथ कम्युनिकेट करते हैं तो we communicate through a speech signal, and that speech signal is basically vital for any sort of human communication, whether it is taking place using any media whatsoever. इसी तरह से अगर आप इंटरनेट की बात करें तो इंटरनेट से जो आपको इंफॉर्मेशन मिलती है, चाहे आप कोई वीडियो इंटरनेट पे देख रहे हैं या कोई आप जो है वो अपनी ईमेल चेक कर रहे हैं या और इस तरह से कोई वेबसाइट एक्सेस कर रहे हैं, सो that information which travels to you on the internet also travels in the form of signals. इसी तरह से अगर हम एक और एग्जांपल लें तो जब कोई डॉक्टर किसी पेशेंट के कुछ वाइटल साइंस चेक करते हैं, फॉर एग्जांपल ब्लड प्रेशर चेक करते हैं या टेम्परेचर चेक करते हैं, जिससे वो ये बता सकते हैं कि वेदर दैट पर्सन इज़ हेल्दी और अदरवाइज, तो that information that comes to the doctor is also comes in the form of signals. So signals are everywhere around us. For example, and this is an example of discrete signals. Discrete और continuous क्या होते हैं उनके बारे में भी हम इस लेक्चर में बात करेंगे. लेकिन एक डिस्क्रीट सिग्नल की जो एग्जांपल है वो है स्टॉक मार्केट का डाटा. स्टॉक मार्केट में यू मे नो के एवरी डे कुछ कंपनीज के जो शेयर्स हैं उनकी प्राइसेस में जो चेंज होती है, उस चेंज को अगर आप फॉर एग्जांपल एक मंथ की बेस पे या एक वीक की बेस पे देखें तो दैट विल गिव यू सम ग्राफ, और वो जो सिग्नल है वो आपको ये बताता है कि स्टॉक मार्केट के अंदर जो ट्रेंड्स हैं किसी कंपनी के या ओवरऑल स्टॉक मार्केट का जो ट्रेंड है वो किस तरह से चेंज हो रहा है. कौन सी कंपनीज के शेयर की प्राइसेस इंक्रीज हो रही हैं, कौन सी कंपनीज के शेयर की प्राइसेस डिक्रीज हो रही हैं, या कौन सी कंपनीज के शेयर की प्राइसेस जो हैं वो स्टेबल हैं. सो all this information is also in the form of signal. So signal is something if we define a signal, so any function of one or more variables which conveys you some information is called a signal. Many a times that signal will be the function of one variable, and in that case that is called a single valued function. But many a times signal can be a function of two different variables. For example, if you talk about an image is a function of two different variables, which is the which displays you, which tells you the information content of that image which you are visualizing. That is basically function of two different variables. So signals are signal is something which conveys you any information about some physical phenomenon. So examples, if we talk about the examples of signal, there are a lot of examples. Obviously this list is not complete, but a few examples of the signal include the voltage or current in some electronic circuit. You being the engineering students may be familiar with the voltage and current signals. So these signals which are present at different instances in a circuit, they basically represent a signal. Similarly, flow rate of some liquid or gas in some chemical process is also a signal. A digital image is also a signal, so as digital video or digital audio. And as I earlier talked about that, the stock market index, which tells you the percentage increase or decrease of some company share values, that is also a signal. So signal की बहुत सारी examples हैं जो कि हम हमारे पास डिफरेंट फॉर्म्स में हमारे पास अवेलेबल होती हैं. और इस कोर्स के अंदर जो हमारे पास सिग्नल सिस्टम का कोर्स है, हमने कुछ ऐसी टेक्निक्स डिस्कस करनी है कि हम इन सिग्नल्स को कैसे एनालाइज कर सकते हैं, कैसे इनको प्रोसेस किया जाता है, और आपके पास उसको आप क्या रिजल्ट्स आप एक्सपेक्ट कर सकते हैं जब आप उन सिग्नल्स को प्रोसेस करेंगे. सो न सिर्फ हम इस कोर्स में सिग्नल्स के बारे में बात करेंगे, बल्कि हम सिस्टम्स के बारे में भी बात करेंगे. सो हम सिस्टम्स को भी डिफाइन करेंगे, आज के लेक्चर में तो नहीं, ऑब्वियसली किसी नेक्स्ट लेक्चर में, लेकिन हम सिस्टम्स को भी डिफाइन करेंगे. सो सिस्टम इज समथिंग विच परफॉर्म्स सम एक्शन ऑन योर सिग्नल. You will give some input to that system, and that input would be a signal. The system may change few parameters of that signal. कौन से पैरामीटर्स हैं, कौन से पैरामीटर्स चेंज हो जाते हैं, चेंज हो सकते हैं, सिस्टम क्या एक्शन परफॉर्म करता है. So we will also talk about that when we will talk about the systems. But in this lecture, in this short lecture, we are only going to define, we have in fact already defined signal, which is something which conveys some information, and then in the next few slides we are going to define some broad categories in which the signals can be divided. So if we talk about the signal classification, so signals can be classified on the number of independent variables. For example, as already I talked about that a signal can be a function of one variable, and in that case it is called a single valued or single dimensional signal. For example, the audio signal is a single dimensional signal, and similarly sometimes it is the signal is a function of more than one independent variables, and in that case it is called multi-valued or multi-dimensional signal. Signals can be continuous signals or they could be discrete signals. So a continuous signal is a signal which is defined for continuous independent variable, which is present at every possible value of its independent variable in some interval, you say. For example, if a continuous signal is defined in the interval from say -1 to +1, then that signal will be present at every possible value of t in that interval from -1 to +1. So if a signal, if you have such a signal, then it is called a continuous valued signal or continuous time signal. In fact, continuous time, not continuous valued. Continuous valued is something else. We will soon talk about that as well, but it is called a continuous time signal. However, there are some signals which are only defined for some instances of time, some discrete instances of time, and they are not present everywhere. So such signals which are only present at discrete instances of time, they are called discrete time signals. An example of a discrete time signal is stock market data, where where you have for every day you have this trend. For example, on this particular day the stock market index was this, and some other day it would be that. So basically the stock market index is inherently a discrete signal. However, many signals are not discrete inherently in nature. Sometimes we need to convert a continuous time signal to a discrete time signal for a number of different reasons. And one particular reason, or one important reason, could be we want to store the value of a signal. Since a continuous time signal is defined for infinite values of its independent variable, it is almost impossible to store a continuous time signal anywhere in some computer's memory or in any device, because every device has a finite amount of memory. So you cannot store infinite amount of information in a finite amount of memory. So for that, if you really want to store some signal, and there are a number of applications where we do need to store the values of signal, so we have to convert that continuous time signal to a discrete time signal. A process which converts a continuous time signal to a discrete time signal, that is called sampling. So in the process of sampling, what we do, although we will not discuss that in detail today, but what we do, that normally we take samples of our continuous time signal at fixed interval of time. So for example, one sample you take at t is equals to 0, next sample you take at t is equals to capital T, where capital T could be anything. It could be 1 second, 0.5 second, 0.25 second. Next could be at t is equals to multiple of that, 2t, 3t, 4t. So multiple instances at integer multiples of that capital T, you take the sample of that signal. So by doing this, what we are doing, that we are only recording the values of that continuous time signal at fixed intervals of time, and we are discarding the intermediate values. For example, if we have taken one sample at t is equals to 0 and one sample at t is equals to some capital T, then we have discarded all the values which fall between 0 and capital T. So in this way we lose some information when we convert a continuous time signal to a discrete time signal. A logical question which may come here to your mind, that whether it would be acceptable to lose that information or not. So in some instances this could be quite acceptable, and in some instances it may not be acceptable because you are losing the information. So there is one particular criteria which is called nucleus sampling criteria, which states that if you sample any continuous time signal at least with the frequency which should be at least 2 times the highest frequency content of that signal, you may not lose any information. And if you follow the Nyquist criteria, then it is guaranteed that you will be able to reconstruct your original signal from the given signal, from the given discrete time signal. So obviously there are a lot of details about sampling and quantization and different steps which you need to perform. Unfortunately, that doesn't fall into the category of that doesn't fall into the domain of this course. You will read about sampling and quantization in detail in your next course, which is about the digital signal processing. But at the moment, you should keep in mind that signals could be continuous in nature. Normally they have another name, they are called analog signals, and signal could also be discrete. Sometimes inherently they are discrete, like stock market data, and sometimes we convert a continuous time signal to generate a discrete time signal for further processing by some digital signal processor or some system which is discrete in nature. So this classification or this differentiation of signals were on the basis of independent variable. Sometimes, however, the signal can also be classified, can also be differentiated in terms of the dependent variable. For example, a signal which has a continuous dependent variable is said to be a continuous valued signal. Normally, when we talk about the analog signal are continuous in value, and they are also continuous in time. However, if for example we talk about digital signal, in comparison to that, digital signals are discrete in amplitude and they are discrete in time. So since signal has two different variables, an independent variable and a dependent variable, so on the basis of that if independent variable is continuous, the signal is called continuous time signal. If dependent variable is continuous, it is called a continuous valued signal. Similarly, discrete signal is the one whose independent variable is discrete, and similarly a signal which has discrete dependent variable is called discrete value. And another short name for that signal, which you may have heard somewhere, is called digital signal. So a digital signal is the one which is discrete in time, and it is also discrete in amplitude. So on the basis of independent variable and dependent variable, you can differentiate between different kinds of signals. Okay, so these are the examples of continuous time signals and discrete time signals. This signal, which is x of t, and its independent variable is t. This is a continuous time signal from say t is equals to say minus 35 to plus 35. This signal is present for every possible value of t. No matter how small you select a t, the signal has a defined value at that t. However, in comparison to that, if we talk about this signal, which is x of n, normally discrete signals are represented by x of n, whereas continuous time signals are represented by x of t. So that is a difference in their notation. So this discrete signal x of n, it is only present at the integer indices n. So this signal has a value at n is equals to 0, then it has a value at n is equals to 1, n is equals to 2, n is equals to 3. Similarly, at n is equals to minus 1, minus 2, minus 3. But what is the value of this discrete signal x of n at say n is equals to 0.5? The answer is not 0. The value of this signal is not 0 at n is equals to 0.5. We will simply say that this discrete signal is undefined at n is equals to 0.5. It is not present, it is not defined at n is equals to 0.5, and similarly at n is equals to minus 0.5 or at any value of n which is not integer, this discrete signal is simply undefined. So its value is not 0, it is simply undefined. So discrete signal is a signal which is only present at those values of n which are integer, whereas a continuous time signal or continuous signal is present for every value of t, no matter how small the value of t is. This signal will be present at t is equals to 0.5, at t is equals to 0.49, at t is equals to 0.51, and so on and so forth. So you cannot say that this signal is not present at any value of t. So this signal is present or defined for every value of t from say minus 35 to plus 35, whereas in case of discrete time signal, it is only present at those indices which are integer. So that is the major difference between a continuous time signal and a discrete time signal. There are a few more differences, and we will talk about those differences when we will encounter them. Okay, so another important class of signals which we will encounter in this course are called even signal. A signal or a function x is said to be even if it satisfies the following criteria. If x of t is same as x of minus t for all values of t, then that signal will be called an even signal. For example, here if I say what is the value of this signal at this instant t is equals to 0.5, so roughly its value is around 1 at t is equals to 0.5. Now if I put t is equals to minus 0.5, the value of the signal at t is equals to minus 0.5 is also 1. So for all positive values from 0 to 3, whatever the value of signal, amplitude of signal is at those values of t, it repeats itself from 0 to minus 3. So for example, minus 2.5, it has a value of 2. Similarly, at plus 2.5, it has a value of 2. So such a signal which is symmetric around this vertical axis is called an even signal, and that could also be the case for a discrete time signal. For example, here in this discrete time signal, the value of this discrete time signal at n is equals to minus 3 and plus 3 is same, at n is equals to minus 2 and plus 2 is same, at n is equals to minus 1 and plus 1 is same. So such a signal which is symmetrical around the vertical axis is called an even signal. When we will talk about the Fourier series and the Fourier transform, then this information that whether or not a signal is even or whether or not a signal is odd, which we will talk about in the next slide, that would be very useful information. And a number of Fourier series and Fourier transform properties which we will discuss, they are related to this concept that whether signal is even or not or signal is odd or not. So one class of signals could be even signals, and another class which is present here is called odd signal. So odd signal is defined as a function or a signal is said to be odd if it satisfies this criteria: if x of t is equals to minus of x of minus t for all values of t for continuous time case, and for discrete time case if x of n is minus x of minus n for all possible values of n, then such a signal is called an odd signal. And please remember that an odd signal is anti-symmetric about this vertical axis. So signal which you see from going towards positive t will be a reflection of the signal which will occur here for minus values of t. One important thing about the odd signals are that the value of the signal, if the signal is odd, its value at x is equals to 0 must be equals to 0, no matter whether it is a continuous time signal or a discrete time signal. And that's very logical because because of its anti-symmetric property. Here the signal should be equals to 0. If signal is not 0 at value of t is equals to 0 or at n is equals to 0, it cannot be odd signal. So if you are asked whether a signal is odd or not, the first thing you should check its value at t is equals to 0 or at its value is at n is equals to 0. If the value of signal at t is equals to 0 or n is equals to 0 is non-zero, then obviously it could not be an odd signal. Okay, so now let's talk about some properties of even and odd signal. If you multiply an even signal with an odd one, if you multiply an even signal with an odd one, so you will, as a result of that, you will get an odd signal. So whenever an even signal is multiplied with an odd signal, the result would be an odd signal. Whenever an odd signal will be multiplied with another odd signal with itself or with some other odd signal, the result would be an even signal. And similarly, when even signal will be multiplied with another even signal, the result would again be an even signal. So there is something which is called even odd components of a signal or even odd decomposition. Any signal, before that let me tell you that some signals could be even, some signals could be odd, but there could be some signals which are neither even nor odd. If a signal is not even, it does not necessarily mean that it would be odd. Similarly, if a signal is not odd, it would not mean that it would be even. There could be certain signals which are neither even nor odd. However, one thing which we can do, that we can transform any arbitrary signal xt or xn, if you are talking about discrete, into an even component and into an odd component. An even component of any arbitrary signal xt is defined like this: 1 over 2 x of t plus x of minus t, and similarly odd component is half x of t minus x of minus t. In the next slide we will talk further about this even odd decomposition. Okay, so even part of a signal can be defined as 1/2 xt plus x of minus t, and odd part of continuous time signal xt can be given as 1/2 xt minus x of minus t. So any arbitrary signal x of t can be converted into an even component and an odd component, and this decomposition could also be important. We will talk about it when we will talk about the properties of Fourier series and Fourier transform, but at the moment you must remember that any arbitrary signal can be converted into an even signal and it can be converted into an odd signal. Okay, so now let's talk about let's take one example. How do we do this even odd decomposition? So let's suppose we have a signal xt which is given like this. X of t is cosine t plus sine t plus sine t cosine t. So this is our xt. This signal is neither even nor odd, but what we are going to do in this slide, we are going to decompose this signal into an even part and into an odd part. So okay, so what we wish to do, we wish to decompose it into its even and odd components, or into its even and odd parts. So to do that, what we will define x of minus t. And how we define x of minus t? Simply we will replace t with minus t in this equation 1. So everywhere wherever there was a t, we have replaced that with a minus t. जहाँ जहाँ पे भी आपके पास t था, आपने उसको minus t से replace कर दिया. But now cosine of minus t is same as cosine of t. Cosine of minus theta is same as cosine of theta. Cosine is an even function, and sine of minus t is equals to minus of sine t, or sine of minus theta is minus of sine theta. Sine is an odd function. So if we use these relationships in this equation, we can write it like this. X of minus t will be cosine t, because cosine of minus t is same as cosine of t. Sine of minus t is minus sine t, so ये प्लस इस प्लस की जगह पे यहाँ पे माइनस आ जाएगा. एंड सिमिलरली यहाँ पे भी ये साइन ऑफ माइनस टी इज माइनस साइन टी, सो ये माइनस यहाँ पे आपके पास आ जाएगा. सो नाउ वी हैव टू इक्वेशन. This is equation 1, which is xt. This is equation 2, which is x of minus t. Now we will add them and we will divide them by 2. If we add them and divide them by 2, we will get the even component of this signal, and you can confirm the even component of this signal will simply be equals to cosine t. And if you want to obtain the odd component of this signal, the odd component can be obtained by subtracting this equation 2 from equation 1, because odd component by definition is x of t minus x of minus t. So if you do that, you will get the odd component, and that odd component will simply be equals to sine of t plus sine of t and cosine of t. So any arbitrary signal which is neither even nor odd can be decomposed into an even component and an odd component. Okay, so now let's talk about something else. We have talked about the even odd decomposition, and even odd was the first classification on which signals can be differentiated from one another. Another set of classification, another thing on which the signals can be classified or differentiated from each other, is their periodicity. Periodicity means that some signals are such that they repeat themselves. There are some certain signals which repeat themselves after some certain amount of time. So if xt is some signal, continuous time signal, so it is called periodic signal if there exists a capital T after which it repeats itself. So if x of t is same as x of t plus capital T, so then such a signal is called a periodic signal, and t, capital T, after which it repeats itself is called the fundamental period of that continuous time signal, and the reciprocal of that fundamental period 1 upon t is called the fundamental frequency of that particular signal, and that frequency is normally measured in cycles per second or hertz. There is another frequency which is called angular frequency, and that angular frequency is defined by this. It is denoted by omega, and that is defined as 2 pi over t, and its units are radian per second. So inherently there are certain signals which are periodic, which repeats themselves after some fixed amount of time, capital T. So such signals are called periodic signals. Periodicity is an important property of signals, and basically when we will discuss about the Fourier series, we will discuss that Fourier series is exists for those signals. Fourier series representation is possible for those signals which are periodic in nature. So certain signals are in fact periodic in nature. However, there are certain signals which do not repeat themselves, and such signals which do not repeat themselves are called aperiodic signals. So signals can be classified on the basis of their periodicity, whether or not they are periodic. So either they would be periodic, or they would not be aperiodic, or they would be aperiodic. So there are just two categories. Either they would be periodic. If they are not periodic, they would be aperiodic. Unlike even odd, signal could be even, could be odd, and signal could also be neither even nor odd. But here there are only two possibilities. Either signal will be periodic. If it is not periodic, then it would be aperiodic. So same concept which we discussed for discrete time periodic signal, almost similar concept is there for, the same concept which we discussed for the continuous time signal, that similar concept is also there for discrete time signal with a slight difference. I will talk about that difference, but definition of discrete periodic signal is similar to the continuous time periodic signal. So discrete signal xn is called periodic if x of n is same as x of n plus capital N for some integer value of n. So it is almost a similar definition as we had in the continuous time case. However, there is a very subtle difference here. Sometimes we will not be able to find an integer value of n after which the discrete signal repeats itself. And if it is the case that we are unable to find an integer value of capital N, then discrete signal will be aperiodic. In continuous domain, this is not the problem. This capital T could have any value. It could be 1.5, 1.25, 1.35, 3.35, whatever. Capital T could have any value. There is no restriction on the value of capital T to be integer. But here there is a restriction. If you cannot find an integer value of capital N, it simply means that your signal will not be periodic. There is also fundamental angular frequency for discrete time signals, which is defined as omega is defined as 2 pi over n, and it is measured in radians. Okay, so in this lecture we talked about signals. What are signals? Signals are basically signals are basically a means to convey information. They could have different types, but all signals convey some sort of information in some form. Then we talked about various type of signals like continuous time signals, which are defined for every possible value of their independent variable, and discrete time signals which are only defined for integer values of independent variable. And we talked about even signals which are symmetrical about the vertical axis. We also talked about the odd signals which are anti-symmetrical about the vertical axis. Then we talked about the even odd decomposition, where an arbitrary signal can be decomposed into an even part and an odd part. And in the last we talked about periodic signals. These are the signals which repeat themselves after some fixed amount of time, and aperiodic signals which don't repeat that. In the next lecture, inshallah, we will discuss about further classification of signals. We will talk about something which is called an energy signal. We will also talk about power signals, and some signals are called energy signals, some signals are called power signals. So for that we talk about in the next lecture. Hope you enjoyed the lecture. Take care and Allah Hafiz.